Jordan. All right, so we're very glad to have Elena Dimitriadis Bermejo, hopefully I pronounced it right, from Toulouse, with a new model for DG categories. So thanks for coming, and you can start when you're ready, Elena.
Thank you. So before I start, I wanted to thank the organizers of the seminar for inviting me. So the work I'm going to present today is actually my PhD thesis, which I defended in like December of last year. And it involves finding a new model for DG categories. So DG categories have been used in algebraic geometry a lot for quite a few years now. But of course, like everything else, they're not perfect. They have their issues. One of the bigger issues is that they have a model structure and they have a monoidal structure, but the two of them are not compatible. So in recent years, people have been trying to find different ways of getting around this problem. And one of them is finding a new model for DG categories. So in order to do that, we take a lot of inspiration from infinity categories. So before I dive into DG categories, let me have a moment to look at how infinity categories work in this context. So one of the reasons for infinity categories is localizations. What do we do when we want to look at a category up to something more fine than equivalences? The classic example would be homotopy classes. So in 1967, Quillen introduced model categories as a way to solve this issue. And model categories work very well, but they also ask us for a lot more information. We need fibrations, we need cofibrations. It's a lot, and it's also information that we lose the moment we do the localization. So other people thought of other ways to work around this. So in 1980, Dwyer and Kahn introduced simplicial localizations, simplicial categories, which are good, but have the same issue as DG categories. They have a model structure and a monoidal structure, but no monoidal model structure. So we have other options. So in 73, Vordam and Vogt introduced quasi-categories. In 89, Dwyer, Kahn, and Smith introduced single categories. And lastly, in 2001, Resk introduces complete Siegel spaces. Now, we would have to wait all the way until 2007 for Berner on one side and Joya-Lanterni on the other to prove that all of these are actually models of infinity categories and they are all Quillen equivalent. Now, if infinity categories have been around for a while, DG categories have been around for even longer. We can find articles using them all the way back in the 60s. But we would have to wait all the way until 2005 for Taboada to construct a model structure for them. So, as I said, some researchers in the last few years have been trying to find other models for DG categories. So in 2013, Kohn proves that DG categories are equivalent as quasi-categories to K-linear quasi-categories, which is a great result, but also K-linear quasi-categories are not exactly easy to use. So as a way to make things simpler is perhaps not the best tool. And then we have, in 2020, Bacard defines DG Siegel categories. And in 2022, September of last year, very, very recent, Mertens defined DG quasi-categories. Now, one thing that we have to be careful about here is that I have been saying that these are models from DG categories, but that is a little bit of a stretch. For now, there are no proofs that any of these models are equivalent or are equivalent. The K-linear quasi-categories are equivalent only as quasi-categories. And also, in fact, outside of DG categories, we don't even have a model structure for any of them yet. That is still work in progress for all of these. Now, if you have been following the last couple of slides, you will notice that we have DG quasi-categories, we have DG categories, we have single DG categories, but we don't really have a linearized version of complete Siegel spaces. So my work will be in that empty corner on this table. Can we find a DG equivalent of complete Siegel spaces? Of course, I don't do this just because I like to have my tables full. Also, because complete Siegel spaces form a presentation by generators and relations of infinity categories. And that would be a very nice tool to have in the context of DG categories too. So now that we've finished the introduction, how is this talk going to go? So first, we're going to give a couple of basic definitions of things that we will be using over the course of the talk. Then we will define DG Siegel spaces and complete DG Siegel spaces. Thirdly, we'll try to do a sketch of the proof of the equivalence between complete DG Siegel spaces and DG categories. And then if we have time, I will go into a few perspectives and things that we could do with this. So let's start with the prerequisites. So first of all, we fix K to be a commutative ring. And then we define T to be a DG category if it's a category enriched over the category of co-chain complexes. So what that means is instead of having sets of morphisms, we have co-chain complexes of morphisms. Now, we want a model structure, and for that, we need at the very least to define the weak equivalences. For that, we will use the homotopy category of T. So if we have T a DG category, we define its homotopy category to be a category with the same objects, and between every two objects, the cohomology in degree 0 of the co-chain complex. And so we say that F is a quasi-equivalence if the induced morphism in the homotopy categories is essentially surjective, and for every two objects, the induced morphism on the co-chain complexes is a weak equivalence. And there's a result by Taboada that tells us that the category of DG categories admits a model structure in which these are the quasi-equivalences, and it is also cofibrantly generated. Okay, so we have our category of DG categories with its model structure. Now, another thing we will be using is free DG categories. So we denote by GR of say K the category of graphs over co-chain complexes. Then we have a equivalence junction between the graphs and DG categories. And we call a free DG category a category that is an image of a graph by this adjunction.
Sorry, does a graph over cochain complexes mean like a set of objects and for any two cochain complex between them? Or
I am not entirely sure I understood the question, but I think the answer is yes. Instead of having like an edge, you have a cochain complex in
That's
between.
What I mean.
Yeah, exactly. Yes. Sorry, I thought of saying that and I forgot. So thank you for reminding me. So yeah, so we have a free DG category is basically we add the composition to our graph. And then we say that a graph is of finite type if it has a finite number of vertices and the edges between two vertices are always perfect complexes. And so lastly, we say that T is a free DG category of finite type if it's free and the graph is of finite type. And lastly, the last construction we're going to need, so don't get scared by the block of text. I just wanted to have the entire construction. So this is Duggar's universal model category. So the only thing we need to remember about this is that if we have any category and any model category, we can construct the category of functors, of contravariant functors to simplicial sets. And we have a Quillen adjunction of this form. And especially we want to remember that Sing is just the map. Okay. What? I have a lot of reverb.
Sorry, no, he's asking what a closed model category is, but I think that's just a model category. Quillen talked about model categories.
They're just the same thing.
So it's
so
just,
yeah. So this
Yeah. It's also really not important for what I'm going. I really just need this Quillen adjunction. But yeah, so that ends the prerequisites. So the next step is to see what complete Siegel spaces are and how we can link them to DG categories. So complete Siegel spaces form an adjunction of this form. So they're simplicial spaces, so contravariant functors from delta to simplicial sets. And what we're going to do is we're going to exchange that delta for this thing. So instead of having functors from delta up to simplicial sets, we have simplicial functors from this to simplicial sets. So what is this thing in red? Well, first we will denote the full subcategory of DG categories of cofibrant free DG categories of finite type by CL. Now, I won't be talking about these words will all come together at all times during this presentation. So I will probably just say free DG categories just because it's shorter. So at any point, if I say free DG categories, I mean cofibrant free DG categories of finite type. Okay. And then we will take the set of quasi-equivalences of DG categories. We construct the simplicial localization. And we define the simplicial free DG categories to be the full simplicial subcategory of that localization, whose objects are the ones in CL. So that is the CLS that we will be using. And now with that, we have enough things to see what our adjunction will be. Okay, so let me talk you through this diagram. So first, we have this adjunction, which is induced by the inclusion. This adjunction, which is induced by the localization. And then this adjunction, which is the Duggar's universal model category. Now you might be wondering, okay, then why don't we just compose this way and have our adjunction? The problem is that these adjunction in this one don't go in the same direction. So they're not actually composable. So to avoid that, we will factorize sing to go this way and just avoid the L on the other side. So our adjunction will be just going straight up in one direction and composing like this in the other direction. Now, this is mostly technical details. In terms of intuition, if you think that sing is just map, that should get you through this presentation. So we have the adjunction. Now the next step is, what is the image of that functor sing?
I'm sorry, can I ask again?
Yep.
What are the objects of CLS again? I just sort
of... CLS,
yeah.
So we start, CL is cofibrant free DG categories of finite type.
Mm-hmm.
Then we do the simplicial localization of DG categories by the quasi-equivalences.
Mm-hmm.
And we take the full simplicial subcategory of the free DG categories of that.
Okay, yeah, thank you.
Is that okay?
Yeah.
Perfect. Okay, so now we want the images of the of sing. So we define DG Siegel spaces. So we have a functor in this category, and we say that it satisfies the DG Siegel conditions if it commutes with, well, it sends co-products to products. If the image of the initial object is a point, and then we have this little construction. So for now, you don't have enough information to understand this. So give me a second to walk you through this. So if we have a graph of cochain complexes, we have alpha a cocycle. We defined the graph G of alpha to be a graph of complexes which has the same objects, the same complexes of morphisms outside of X and Y. And in X and Y, we just add a little beta whose image by the differential is alpha. So we're basically killing alpha in a way. And we can see that that is the same thing as saying that G alpha is the push forward of this diagram, where Kn is a graph with n points. No, it's 2 points, and the complex between them is 0, except for of degree n, where it's k. in case, say, n is the graph with 2 points and the complex is 0, except on degree n and n minus 1. So now that we have this definition, we can go back to the definition of a DG-Siegel space. So we say that F is a DG-Siegel space if it commutes with coproducts. The image of the initial object is the point, and the image of the free version of G alpha is a homotopy pullback. Okay. Now, once we have the correct definition of a DG space, DG-Siegel space, it is relatively straightforward to prove that we have a simplicial model structure in which these DG-Siegel spaces are the fibrant objects. This is just a left Bousfield localization. And so we call this model structure the DG-Siegel model structure. Now, we have been working pretty close to Resk's original paper on Siegel spaces up until now. So anyone familiar with that paper won't be surprised to discover that we quickly realized that this is not enough to be a model for DG categories. There is a kind of morphism that should be invertible, but isn't. We have the exact same issue that Resk had in his paper. So we're going to have to define complete DG-Siegel spaces. And in order to do that, we're going to first make a comparison between DG-Siegel spaces and classic Siegel spaces. For that, we have a morphism. It's called the linearization of the delta between delta and our free DG categories, in which for every n, we associate a DG category with n points and the complex in between every two of them being 0 everywhere except in degree 0, where it's k. And that defines as a equivalent adjunction between simplicial spaces and our functors category. And so we call the functor that goes in the other direction the delinearization morphism. Now, apparently we've been doing things the right way. If we take a DG-Siegel space, then its image by the delinearization functor is a classical Siegel space. We haven't gone very far, which lets us define complete DG-Siegel spaces just using classical complete Siegel spaces. So we say that F is a complete DG-Siegel space if it's a DG-Siegel space, and its image by the delinearization functor is a complete DG-Siegel space, complete Siegel space in the classical sense. Now, there is a way of defining this without using the delinearization morphism. I haven't put this in the slides, but it is relatively simple. So we don't need to end up doing all our calculations in simplicial spaces.
Yes, you want to apply the left adjoint J lower star to the morphism in the category of Siegel spaces, is it? Like usually for a complete Siegel space, you have the map from, I don't know, one to the nerve of the free isomorphism or something, and if you view that as living in the category of simplicial spaces, then you can apply this left adjoint J lower star or J shriek to that and define things by adjointness. Does that sound correct or no?
Yeah. Again, you're kind of garbled, but the parts I got, I think that is pretty much what we did.
Okay. I guess I just mean that if you define the complete DG Seagull space using the J upper star, the delinearization, that's you're applying defining something by a right adjoint, but you can also use the left adjoint applied to the sort of generating morphisms in the classical Seagull for complete Seagull spaces, and somehow you can use the left adjoint instead of the right adjoint. That's my guess. That's all.
Yeah, there's a lot of that, honestly. There's a lot of going back and forth for all this. So yeah, absolutely. Yeah. It's so we have so we define a complete DG space in this way, and all of this was to try and find the image of the functor Sing. So we will be happy to know that the image of every DG category by the functor Sing is actually a complete DG space. And lastly, on this section, we can prove that there is a simplicial model structure on our functor category whose fibrant objects are the complete DG Seagull spaces. So yeah, to add to your question, for this proof, we go back and forth between, we use the adjunction in both senses, like in both directions multiple times. So yeah. Okay. And so this is also a left Bausfield localization. And we call this the complete DG Seagull model structure. Now, I said that the reason we go to complete DG Seagull spaces is because there's there's a type of morphism that should be an equivalence but isn't. So now it's the time to see what are those. So there are these ones. Now, for now, you cannot understand the details of this definition yet. You don't have the definitions for it. I just wanted to put it up because it looks very similar to the definition of weak equivalence in DG categories. And that is not by accident. If both F and G are the images of Sing, this is literally the definition of a weak equivalence in DG categories. So let me try and define all the things that I am using in this definition. So first of all, if we have a DG Seagull space and we have X and Y, two objects in the P0 of the image of K, we define a covariant functor between cofibrant cochain complexes and simplicial sets, such that for all E cochain complex, we have the homotopy fiber of this diagram, where E of XY is a DG category with 2 points, and the cochain complex between them is 0 everywhere except at degree 0 where it's E. And so we call f of xy the DG mapping space of f at x and y. Now, this definition is less daunting than it sounds, because we can prove that fxy is always representable. So there exists an actual cochain complex fxy with this condition. Now, of course, by Yoneda, if f is sing of t, f of xy is just t of xy. So we find back the normal DG category. So because this is representable, I will be using DG mapping space interchangeably, either for the functor or for the cochain complex. So now the other things, if we have a DG single category, we call the homotopy category of F, and we denote it by bracket F, a category whose objects are the P0 of F of K, and whose morphisms are the cohomology groups in degree 0 of the DG mapping spaces. By the way, if at any point I talk about the objects of a DG single space, this is what I mean. I will try not to, but I do have that tendency. So now we have all we need to define a DK equivalence. So we say that F is a DK equivalence if the induced map on the homotopy category is essentially surjective, and for every 2 objects, the induced map on the DG mapping spaces is a quasi-equivalence. By the way, this should be just the cochain complex. I forgot to change that. Okay. And now is where linearity comes back to bite us. What we want to is to say that F is a DK equivalence if and only if it is a weak equivalence for the complete DG single model structure. And this is quite hard. So for now, it's a hypothesis. I will come back to this later, but for now, we're going to just assume this is true. And now, assuming that hypothesis, we're getting to the proofs. So I'm going to try and give you an idea of how we prove that this adjunction is actually an equivalence. So let's start with the fully faithfulness. Now, the general idea behind this proof is that it is relatively easy to prove that the functor sing is fully faithful on 3 DG categories. So what we're going to do is we're going to try and chop all DG categories into 3 DG category bits, and then use the fact that all of the bits work correctly. So how are we going to do that? We're going to be using hypercovers. Now, hypercovers are a tool that is used in a lot of different contexts, but to our chagrin, none of the definitions that already exist work in our case. So we had to define a new one. So if we have M a model category and M0 a subcategory of it, we define F to be an M0 epimorphism if for all X in M0, the morphism, like the P0 of the maps, is surjective in simplicial sets. So we say that an augmented simplicial object is an M0 hypercover of X if for all natural n's, this functor is an M0 epimorphism. Okay. So, okay, having a definition for a model category is nice, but do we actually have these in our case? Can we construct a DG, a free DG category hypercover of any DG category? And the answer to that is yes. So if we take M to be the DG categories and M0 to be the free DG categories of finite type, then for all T DG category, there exists a hypercover made entirely of free DG categories. Now, if you read the entire slide, that is not exactly what I'm saying. We have to fix points, but that is a completely technical detail. So I'm just going to sweep it under the rug for the interest of this idea. There exists a hypercover, and that is all you need to remember. So, okay, there exists a hypercover. So can we say that it is actually chopping the original DG category? Yes. So we have this result that says that if we have a hypercover constructed this way, then the homotopy co-limit of the augmented object is weak equivalent to the original object in DG categories. And now the other thing that we had said is that, okay, if we restrict ourselves to 3 DG categories, then the functor thing is fully faithful. Okay, so we just need one more lemma before we can do the proof of the fully faithfulness. So we say if we have a hypercover constructed like this, then the homotopy co-limit of the image of the hypercover is dk equivalent to the image of the original object. And now we have enough to prove that the functor is fully faithful. So assuming the hypothesis to be true, we have this diagram. So let me talk you through it. So first we have this arrow. So we said that homotopy co-limit of sing of ti is dk equivalence to sing of t. So assuming the hypothesis to be true, that is a weak equivalence, and it's imaged by ray, still a weak equivalence. This is a weak equivalence because RE is a right adjoint. And this is a weak equivalence because the TIs are all free DG categories of finite type. And we said that for those, sing is fully faithful. So this is a weak equivalence, this is a weak equivalence, but by 2 out of 3, this is a weak equivalence, and our functor is fully faithful. Okay, so the last thing we need is the essential surjectivity. And this is going to work in a really similar way. So we will also be using hypercovers to find a DG category whose image by sing is DK equivalence to our DG zero space. So we need another definition of hypercover. So a morphism between two DG single spaces is a DG single epimorphism if the morphism on its objects is an isomorphism, and also the induced morphism in the DG mapping spaces is a split epimorphism. And now, if we have F a DG single space and an augmented simplicial object, then the augmented simplicial object is a DG single hypercover of F if for all n naturals, this functor is a DG single epimorphism. And now, again, we can chop things to bits. If we have a DG single space, there exists a simplicial objects in DG categories whose image by sing makes a DG single hypercover in DG single spaces. So in other words, we can construct a DG single hypercover of any DG single space that is made of objects in the image of sing. And I'm not going to give more details than that. If we have F a DG single space, then the sing in this theorem is going to be the sing of the homotopy co-limit of the T's in the hypercover. Again, we can't prove that this is a weak equivalence. We can only prove that this is a DK equivalence, which is why, again, we need our hypothesis to be true. So if we assume the hypothesis to be true, then the functor sing is essentially surjective. And we have an equivalence of categories. And we are done. This is actually a model, and everything is good and well. I don't know how much time I have left because I didn't check the time before I started.
Got 5-10 minutes if you want.
Oh, cool. Then I can go into some perspectives. Great. Okay, so obviously the first thing that we need to do now is how do we solve this hypothesis? Now, this is something that arrived in Resk's case when he was working with traditional complete single spaces. So what he does is he creates a functor that associates a complete DG single complete single space to any single space, and it has this form. The problem is that in order to define this, we need to be able to define this exponential. And to define that exponential, Resk uses the direct product on simplicial sets. Except that, as we have said before, in the case of DG categories, the monoidal structure and the model structure are not compatible. So that exponential is not well defined for us. So in order to finish this proof, we will need to define a monoidal structure in complete Siegel spaces that is compatible with the model structure. So that is why this is being a little bit harder than it was in Resk's case. Now, another possible prospect of this. So 3D Siegel spaces were not our first idea. In origin, we were trying to work with this thing called a linear simplex category. So if we have n a natural number, and we have s and n to be n-uplets of integers and natural numbers, respectively, we call delta k of nsd a dg category with n+1 objects, and in between every two of them, a complex concentrating degree Si, where it's k of di. So the idea is the delta k nsd is of this form. And so we denote the full subcategory of DG categories composed of this by delta k. And we call that the linear simplex category. And if you have been following, we have actually encountered these delta k's quite a bit. On one hand, they're all 3DG categories. So that is a good point in our direction. We also use delta k of 1 and 1 in the definition of DG Siegel spaces when we define G of alpha. And also the image of the linearization functor gives only objects in delta k. So all of this makes us think that there's probably a way to define complete DG Siegel spaces using only delta k. That will probably require quite a bit of work, but we think it would work and it would be interesting to look into, as delta k would be a really nice set of generators. And then a couple of more far away prospects. So one of the interesting things about complete Siegel spaces, the classical ones, is in an article from 2004, if I remember correctly. Toen used complete Siegel spaces to compute the group of automorphisms of infinity categories. We found that the only the group of automorphisms is just Z over 2. We have the opposite and that's it. And so because complete DG Siegel spaces are a kind of presentation by generators and relations, we could probably use it to calculate what the group of automorphisms of DG categories is. So it will definitely not be as easy as Z2 because we have linearity. So at the very least, we need the group of automorphisms of K. But it will probably be doable and would be an interesting result to have. And then just an open question. There are a lot of different definitions of hypercover. There's hypercovers in topological spaces, in simplicial spaces, in infinity categories. I have 2 different definitions just on this presentation, and they all look really, really similar, and they all have pretty much the same properties, basic properties. So I can't help but wonder, is there a unifying definition of hypercover? can we find a definition of epimorphism that lets us define hypercover in a general sense that englobes all of these? So this is less an idea and more of a thought, I guess. But that is something I have been thinking about and I wanted to share. And with that, I am done with my presentation. So thank you very much for your attention. And if you have any questions, I am here to answer.
Thank you. So any questions? Maybe shout them out probably, because I think she doesn't hear the back of the room very well probably. But if you have any questions, go ahead. So can I ask a question then? So you have the linear simplex category, and then you have this CSG, which is this bigger thing. And what are the better properties of why do things work better or more easily if you have CSG instead of the linear simplex category?
Okay, so that comes back to hypercovers. It's just that in order to be able to construct hypercovers, we needed the so I'm trying to find the exact result so I can give you the exact. So in order to be able to say there exists always a hypercover, we needed for every object to be fibrant, and also for the subcategory to be closed for finite coproducts. And that is not the case for delta K. Mm-hmm. So technically, we could have used just the closure, mm-hmm. but that gives us a subcategory that's quite abstract in its definition. So we thought it was probably easier to manipulate to have 3 DG categories. Mm-hmm. So the basic reason is that delta K is not closed for finite coproducts.
Mm-hmm. I see, thanks. One other question, I think this is probably completely wrong headed question, but somehow, because when you pass from simplically enriched categories to complete Seagal spaces, you're moving from sort of categories enriched in some V to functors into V.
Yeah.
Right. So somehow I'd imagine that in this setting, you're moving from V categories to functors into V, which would be DG. So can you do something? Can you look at some sort of diagrams in DG? Is that the wrong thing?
It is not the wrong thing. It is just a different approach. Mm-hmm. If you look, for example, that is a lot closer to what Bakar and Mertens are doing.
Okay.
So they are a lot more just changing the if anyone speaks French, l'ensemble d'arrivée. I am blanking on how to say that in English. The place we're going, the place that functors are getting to.
Codum in.
Target.
Yeah.
Yeah. Thank you. So they're doing a lot more of like changing simplicial sets for something that's linearly enriched. Mm-hmm. We didn't go that route. Mm-hmm. First, because we thought delta K would be enough. Mm-hmm. So that would be much simpler. 2, because simplicial sets are very well known and very easy to use. Mm-hmm. So we thought it would be interesting to keep it there. Mm-hmm. And I think also just because the idea was to make something that would be easy to use for algebraic geometers.
Mm-hmm.
And 3D categories and finite type, these kind of things, something that they use a lot. So it was probably easier to go that route than as an application thing. But it is not wrong. It is just a different point of view. And if you're interested in that, probably Mertens would be closer to what you're thinking.
Okay.
Is DG quasi categories.
Okay. And does your approach then, if it's all sort of your approach is all based in simplicial sets, then does that mean like you could possibly get a Cartesian monoidal model structure, or like with just ordinary Cartesian products, or is that not possible? So just the Cartesian product of two complete DG Seagal spaces.
We think so. That I think comes back to this issue.
Right.
So yeah, we need this monoidal structure. It's been a thorn in our side for a while. If we manage to do this, and I don't see a reason why we couldn't, just need to find the right way to tackle it. I think we could. I really think it could be done. And if you have any ideas on how to tackle this, I am open to all of them.
It's probably not relevant, but so I'm very vaguely aware that someone defined a skew monoidal structure on DG cat. So it's a variation of a monoidal structure which has some, the associators aren't invertible and stuff, but I remember there was a paper about it last year, and it might have, I don't know if it would be helpful to have some other monoidal structure on DG cat with some better properties that you could, and maybe you could use that, but
yeah, maybe
was,
it's I will look into that just in case.
Yeah,
can never have too many leads.
Yeah, I don't know. Does anyone else have any, or are there any more questions or comments? Well, if not, then thanks very much for the talk again. And yeah, so next week I think we'll have Miloslav is going to give a talk. So here we have another talk, and yeah. So thanks very much for coming and giving the seminar. It's very enjoyable. So,
thank you for inviting me.
So yeah, it's a pleasure. So so I'll stop